Our next speaker is Kenia Picos. She is a full-time professor at CETES Universidad at the Escuela de Ingeniería Campus Tijuana. She received her PhD degree in 2017 from the Center for Research and Development of Digital Technology of the Instituto Politécnico Nacional. She concluded a postdoctoral research in 3D pose estimation with artificial intelligence in Madrid, Spain in 2018. Her current research interests include computer vision, object recognition, three-dimensional object tracking, pose estimation, and parallel computing with graphics processing units. I give the word to Kenia Picos.
Good morning. Thank you very much for the presentation. Thank you very much. My name is Kenia Picos, and this work I'm working in this proposal in collaboration with Dr. Ulises Orozco. We are continuing exploring about cucumber inspection for quality control in a production facility. First, I want to start with the introduction and then some interesting facts about agriculture produce in Mexico. Then we are going to talking about our proposal method for cucumber inspection, experimental results, and then our conclusions. For a brief introduction, agricultural industry exports a large amount of fruits and vegetables in the country, which require a good classification and selection for quality control. In this case, this process is commonly carried out manually, where workers visually verify if the product has defects that, for example, has an appropriate size, volume, even texture of the surface of the cucumber. Color, for example, is very important for its final packaging. We are concentrating for cucumber inspection for export, because it needs to be more appealing for export. In some industries, this is carried out semi-automatically. In these cases, some farmers inspect visually the produce, but even in the production, in the facility, is another inspection with industrial cameras, but always has the risk of not meeting the quality specifications. So in this proposal, we want to inspect more cases, extend our work. We are going. We're working in this project for several years, and has. First, we have a little bit of progress, but in this now this problem is very interesting for us, with new computational techniques. So in this work, we explore more complex cases of cucumber diseases, such mold, ripeness, rot, cut, scabs, stains, spots, for example, discoloration on the surface of the produce. A classification system is proposed to inspect the quality of cucumbers, distinguishes between good and defective products. We address significant strategies to solve the problem as follows. For example, the first contribution is maybe it's a little bit straightforward, but it's consume a lot of time of our team, is to create a new database. So we generate a database specific for this problem, which illustrate different cucumber diseases. This is quite difficult to have. Another thing is the cucumber classification. Now we are using a more advanced artificial intelligence methods, for example, vision transformers, and then we implement data augmentation strategies. This is some examples of the cucumber captured on site in the industrial facility. Excuse me. For example, in these images, more than one cucumber is present in the image. Another thing, we have the background. The background are the rollers of the conveyor belt. So we need to try to extract that and try to separate all the cucumbers to inspect individually. Some of interest facts about cucumber production. In Mexico has a very insignificant production for these products. Is a very contribution in Mexico. Mexico ranked number top 5 in world production of cucumber and number 1 in Latin America in 2020 of cucumber. So total annual production of 1 million tons of cucumber per year, and 80% is used for export. And an interest fact is Mexico is the largest exporter of fresh cucumber. For example, for the US or Canada, needs for fresh cucumbers. And also, cucumbers, for example, cucumbers are mainly eaten raw, but nevertheless, they can be processed. For example, in other countries, the export could be with a product with added value. For example, pickle, juices, skincare products, or scents. So our proposed methodology is very straightforward in concept. First, we have a video capture, for example, for the industrial camera. The camera is placed in top view of the conveyor belt, so we can see in the input images several cucumbers per image. So we have this input image, then we have an input normalization. We prepare the data for our algorithm. We need to implement data augmentation because the data set is relatively small. And we implement an artificial network model. Our previous proposal includes convolutional neural networks, but this time we're going to implement using vision transformers. This architecture is designed for inspecting the quality of cucumbers, of efficiently distinguish between good and unsuitable products to export. The proposed methodology is composed of 3 main steps: input, normalization, data augmentation, and our proposed model. So for this work, we generate our own database of cucumber images. Data collection was conducted within the agricultural facility. Top view captures of cucumber in a conveyor belt with rollers that allow the product to be transported and seen individually. Also, laboratory images we implement. In these cases, we doesn't have enough cucumber diseases in the data set. So we, in laboratory images, we take in to collect samples of defective cucumbers inspected in a more controlled environment. In this case, for example, in this image, as you can see, slight imperfections in color or texture, for example, some bumps in the surface are acceptable in these images. However, we have some images with cucumber diseases, for example, mold, ripeness, cuts, discoloration, etc. In our database contains examples of defective and non-defective cucumbers, which we consider class 0 and class 1 respectively. In total, we have a small amount of image. In this case, we have 119 images with diseases, cucumber diseases, and 324 images of good cucumbers. So we have tried to normalize of the same dimension, and we process in color image, 3-color channel. So as you can see, it's very small, small amount of data we have in this data set. For example, in the first 2 columns, there are examples of defective cucumbers. As you can see, we can have some mold, of ripeness, or some scabs or cuts, for example, or stains, discoloration. Besides the maybe the shape of the cucumber is not some too much appealing for export. No? So we want to this was captured in a more controlled environments, and these are good cucumbers. Mainly in our the industrial facility. So we implement data augmentation. In this case, we have data augmentation for perform more variability in our database in 12 common image conditions. For example, contrast, brightness, hue, color degradation, shear, vertical, horizontal flip, saturation, rotation, sharpness, perspective, zoom, and Gaussian noise. We added to the image in slightly conditions. So because we have unbalanced data, we need to implement all these strategies as a random manner to increment our data. In this case, we have cucumber class 0 of the cucumber, cucumber with diseases. This is the original image captured in our laboratory, and this second column is the augmented data of the left. So this is a version of the original. This is another version with more shear condition. This is another version with, for example, with color or color modification or brightness, etc. So the new synthetic images are concatenated in the dataset as a new input. We also implement the vision transformer model. We design a vision transformer architecture for cucumber classification. The dataset is distributed with 70% training, 10 for validation, and 20 for testing. The VIT applies the transformer architecture to computer vision tasks. Instead of the traditional CNN, we explore that in previous work. The VIT architecture divides the input image into patches as tokens. If you are familiar with a natural language processing, is the same structure of the tokens, but in image, and applies an attention process to understand relationships which connect with the inputs. The proposed VIT model include the following key stages, which are image patching and embedding, positional encoding, transformer encoder, and MLP head, which is a multi-layer perceptron head. VIT are the state of the art at capturing long dependency across images, which are very interesting to implement in our problem. However, commonly requires a large data set, which we are not having that in this case, to train, and higher computational complexity. In this paper, an image is worth 60 by 16 words. In this paper explains with a lot of detail, all the image that inputs that vision transformer. In this case, we have we have an input image, which are separated in patches with a linear projector of flattening patches. We have a position embedding for our transformer encoder with both of the classes, class 0 and class 1, which are our defective and good cucumbers. Some results. The performance of, we compare with CNN, a classic method of CNN. This comparison is a confusion matrix. For example, we have a limited classification, for example, in defective cucumbers. In this case, we present the loss and accuracy of the training and the validation sets. In this case, we can see that the loss, which is in blue, and the accuracy, which is in orange, could be acceptable performance. However, we have a lot of variations in the validation test. In our proposal, we have the loss and accuracy from through epochs. For example, we have 50 epochs for the BIT model. We have more smooth and more easily to converge to in both cases, in training and validation sets. In this case, the confusion matrix shows that we have a good classification results. Also, we compare the CNN model and the BIT model. We have a good performance in loss in accuracy in different quantity of epochs. Also, BIT in the 20th epoch has a very good performance. However, in time, we have almost the twice of the time, so it's not. We need to keep working on that. In this case, I want to illustrate the loss and accuracy in 100 of epochs. So as we can see, we have a very good performance. Also, with 20 epochs is very acceptable result, and then stabilize to the convergence. So for conclusions, in this proposal, we work in more complex cases of cucumber diseases. This disease could include mold, rot, ripeness, cut, scabs, stains, discoloration, among other problems in the surface. This proposal focus of inspecting visually, inspecting the quality cucumbers using classification of vision transformers, which are capable of distinguish good and defective products. We create our own database with the peculiarity of the specific cucumbers species grown in our country. The database reflects both good quality cucumbers and cucumbers with defects or diseases. Data augmentation strategies are proposed to enrich the data imbalance. This brings image variability in 12 image conditions. And a comparison of the proposed method with the artificial intelligence methods is made to measure classification performance almost with 13% of accuracy improvement of the VIT at the 20th epoch, also with 46% more of the time consumption in training. This current methodology is reliable to implement in real applications for the inspection of the cucumber. This demonstrates that has efficient performance for quality classification and other products, type of products. For me, thank you very much for your attention. Thank you.